first talk about the address spaces. Well, when you think about the CPU here, you may see if I have this. Yes. So when we talk about CPU, okay, and here's my main memory, and you can see that you send in the physical address and you get the data from here and then process it, right? So this is a system that uses physical addressing, and this is used in simple systems like embedded microcontrollers, cars, elevators, and etc. etc. Okay. In this case, your main memory is pretty simple. You have your basically it starts from A to some whatever the size of the main memory, and your data is in here. Okay. So this is kind of what we call physical addressing. Now, what about the virtual addressing? In the virtual addressing, in the CPU essentially works at the level of virtual addresses. It issues virtual addresses. For example, in this case, the address can be 4100. And then we have a memory management unit. So we will see what it means later. Memory management unit, which then translates this virtual address into a physical address, okay, such that you can send it to your main memory, and then you will get. And this is actually what we mean by virtual memory, meaning that your CPU here thinks that it's getting its data from a virtual address at this location, okay, which does not exist. Whereas your memory management unit, it goes here, it maps to a physical address, and then from this physical address, then it returns this value. So your CPU addresses virtual addresses, gets the data. It doesn't know that there is a physical memory that is very different from what it has. Now this is kind of it's if you think of this is a little bit similar to the caching idea that we had, right? In the caching idea, what do? You have you send in an address, right? And with this address, you check your cache. If it's in the cache, you immediately get it. If it's not in the cache, then it's a cache miss, and you have to go elsewhere and bring it to your cache and then fetch it, right? But it's the same idea. The cache is very small, and basically what you have to do is the actual address that you issue is actually, for example, in the case of x86-64, the address bits, you have 48 address bits, which spans a huge address space. But your cache is actually we have seen how big our caches were. It was I think it was in L1, maybe it was 16 kilobytes, right? So you can imagine that on one hand I have this 2 to the power 48 address size, whereas in the real basically cache you have much less basically amount, right? That's basically what we have. So we'll see about how this actually works. So this basically virtual memory system is actually used into most what you call the computers, servers, laptops, smartphones, and this is actually a really, really great idea that has also found that was visualized beautifully in the movie series Matrix. Okay, so let's talk about what we mean by an address space. What we mean by this is that an address space is actually something that's linear. It's basically you have a set of non-negative integer addresses starting from 0 to some number. Okay, and this is what we call as an address space. And then what we have is we have a virtual address space and a physical address space. And in the case of a virtual address space, you can imagine that the virtual address that I have is, for example, it's the virtual address has a number of bits, and so if this address, and if I have basically n bits here, it means that with this I can address my virtual address is 2 to the power n bytes. Okay, right? This is. But then we also have a physical address. And the physical address can and is usually different from your physical virtual address. In this case, it can be you may have a different number of bits, say called as m bits, and hence my physical address space is 2 to the power m bytes. So with this, the challenge is for the virtual memory. The challenge is that you want to map your virtual addresses into physical addresses. Okay, and how do we implement this? Now, why do we use VM or virtual memory? The first thing is, we want to use our main memory efficiently. What we do is we use our DRAM, which is our main memory, as a cache for parts of the virtual address space. Okay, so in the idea, like in the caching idea, remember that we have this cache at the upper level. Okay, and then what it would do is, we know that we have at a lower level, we had this big address, basically this memory here. Let me just call this, this is my memory, okay? And in the case of caching, we would then, the challenge was we have very limited space here. And the challenge is we want to bring in some of these items here, okay? Some of these data in the main memory. I cannot fit all of them, but I want to basically bring in only the ones that I will be using, okay? I will be accessing, in time and space very frequently. I want to bring them in here, okay? So here we have our cache, okay? And the cache is essentially, it's basically bringing parts of the things that are accessed, frequently, okay? That's the idea of a cache. Now, what's different in the virtual memory is, in the case of a virtual memory, we have our, basically, what we will do is we will use our DRAM, and it's again, limited, right? And then, but we will use our DRAM as a cache for the virtual address space, which may not exist, okay, and which is created on demand. So let me see this, you need to draw this in a different way. So we have this virtual, which doesn't exist, never fully exists. And this basically address is essentially created and copied, okay, as needed into your main memory. So this is like in the case of, or for example, let me just give you an example. Imagine that, you are kind of emulating the world. Okay, you would say that, well, I know this world is so big, there are all these different countries, there's China, US, Germany, Australia, there's Antarctica, and then but I would say that, have you been there? Have you checked it, like by physical it? Have you touched the ground? And you would say that no, but I know that it is there. Well, how do you know it? And in the actual physical world, we know that it has. Now, what's the virtual memory, basically implementation of this, or the matrix? It's like this. Imagine that you're building up this world illusion using only a finite amount of atoms or dirt, okay, toprak, okay, or like you have only, for say, a finite amount of, cement or the different elements, okay, which is sufficient to build, say, 1 kilometer, or maybe like say that, 10 kilometer by 10 kilometer patch. Okay, let me just draw this here. So here's my basically world, and on this world, the amount of basically material that you have is essentially like, can cover, I can implement it this patch, okay? That's it. And you can build like in this patch, you can build your buildings and etc. etc. So like when you think of it, like you have been like in Ankara for most of the time, and you can see that, as long as you're in here, it is actually great. But then what happens if you go somewhere else? Like what happens, for example, when you say that I want to move to say Berlin, okay? Like so let's go, this is Berlin. Take the flight, okay? And when you go there, what will like if there is a system, what will it do? What it would do is the following. It would delete, it would use, like, remember, it only can cover this much, create that much space, right? So what it would do is it would then take all this material here, okay? Once your flight takes off, okay? It will remove all the things in here, and then it will build Berlin for you, so that when you land here, you will see Berlin. But when you're in Berlin, how do you know that Ankara still exists? It may not, right? It may still be an illusion, because there's this other thing, okay, in the movie that's called the Matrix, which creates this reality on demand for you. Okay, that's why, like in the case of like this DRAM, okay, when we say it's caching this virtual memory, this whole thing never exists. It's just like in my world, this virtual world, that the world never exists fully. But whenever you decide to take a plane and move somewhere else, then it will dissolve your previous one, and then it will create your new one. And so with this, you can create the illusion that that the whole world, I mean, from your point of view, the whole world exists. Then after that, you take another plane to Sao Paulo in Brazil, and you go there. It is there. But so wherever you go, you know that you can check. But when you go there, then how do you know that Berlin still exists? How do you know that Ankara still exists? Okay, that's the idea of virtual memory. So, Okan, you have a question, but let me just proceed a bit and then I'll comment to yours. So, essentially, it's basically a virtual memory system. It's using DRAM as a cache for parts of the virtual address space. It simplifies the memory management unit, meaning that each process will get the same uniform linear address space, meaning that each process, or like what's a process? Well, process is basically a program in execution. Okay, a program is just the executable, but when you start running it, then we call this a process. So it assumes that it has a linear address space from 000 to FFF. Okay, that's basically what it allows. And it isolates address spaces, meaning that when you have one process, it cannot interfere in another's memory, despite the fact that their physical memory locations are just nearby. And the user program, for example, cannot access privileged kernel information and code. We will learn more about this in the upcoming hours and weeks, and also in operating systems course. So let's just start basically VM as a tool for caching. Okay. Well, conceptually, what we mean by a virtual memory is essentially an array of n contiguous bytes in the disk. So then we say that this is my virtual memory, and we call each block as a virtual page. It's virtual page 1, 0, 1, etc., etc. Okay. And here's your physical memory. And what we do is basically the virtual memory system. It essentially caches some of them into the physical memory. And basically, this is the part, basically we have this is our DRAM. And in this case, we call each of them as pages. So pages, like in the case of cache, for example, and in the case of virtual memory, we have some basically similar terminology. In the case of cache, we have this, data blocks. Remember them? Okay, that's how we move data between different layers of the cache. In the case of virtual memory, we call them pages. It's the same thing. It's the same kind of block. And what we do is essentially, for these virtual pages, like some of them, these pages are actually stored on the disk, and they are brought into the physical memory on demand whenever we need to access them. And these physical pages then basically are stored in the physical memory. So why do we have this? It's because, like in the case of DRAM, okay, well, when you look at remember in our caching case, we had SRAM, static RAM, and the DRAM, and we knew that DRAM was approximately 10 times slower than SRAM. But when you look back here, like let's say that this virtual memory is actually resides on the disk. And actually, in reality, it doesn't fully reside on disk, but most of this reside on the disk, and we will learn more about this. When we talk about disk, remember that and the DRAM, the disk is about 10,000 times slower than the disk. So you can see that if this is my, for example, cache, like we call this the SRAM, okay, and then which is I have DRAM here, and then I have the disk. And the crucial thing is that the disk is about 10,000 times slower than the DRAM. And as a result, once it goes, we try to have a large page or block size, typically 48 kilobytes. And remember that in the case of a cache, we were talking about 64 bytes. Whereas in the case of this virtual memory, we're talking about something 4 megabytes, and it's fully associative, meaning that when you take basically a page from the disk, okay, and then you can basically move it to basically any place on the DRAM, and it requires a very large mapping function. It's very sophisticated and it has some expensive replacement algorithms. And it's too complicated and too open-ended to be implemented in hardware. And it uses write back rather than write through. So we have seen this in the case of cache. So we will discuss basically if you did not understand everything that we have here, but if these we will now uncover them one by one.